Hello, my name is Paula, and today I'm presenting my dissertation entitled An Exploring Study of Designing Applications of Multistream Deep Neural Networks, supervised by Professor Flávio de Barros Vidal. This presentation will be divided into an introduction containing the motivation and goals of this work, a brief theoretical foundation, including the main convolutional neural networks, as well as multi-stream convolutional neural networks. I will also talk about the methodology of this dissertation and present the initial contributions and finding the gap that led to the lattice cross-fusion strategy, showing the results of the technique, and finally the conclusion and future works. In the last decades, machine learning has been gaining prominence both in the academic community and in the industry. Machine learning methods rely heavily on good feature structures, and deep learning is able to learn multiple levels of representation using only pure inputs. Highlighting one of the deep learning techniques, we can talk about convolutional neural networks, or CNNs. They are easier to train, have better generalization, and multi-string convolutional neural networks, or MCNNs, are those CNNs with two or more inputs, and they extend the connectivity of CNNs into other domains. The primary goal of this work is to design, improve, and explore the current models of CNNs and MCNNs, in addition to proposing a new structural model and a model that is able to intermediate all MCNN's processes. And as secondary goals, we have to study, understand, and evaluate traditional and classic CNNs and MCNNs models, in addition to the development of MCNN applications. Also counting on the comparisons of applications with traditional CNN models. Further, proposing new MCNN architectures focusing on improvements based on structural changes and testing the new module using same domain and cross-domain inputs. Usually, CNNs are structured as a series of blocks, where the first block is composed of convolutional and pooling layers. The convolutional layer performs several convolutions in parallel to produce a set of linear activations. In the second stage, each linear activation is run through a nonlinear activation function. Then, the pooling layer modifies the output of the layer further with a pooling function. A pooling function replaces the output of the net at a certain location with a summary statistic of the nearby outputs. These components are summarized in the figure. With the successive blocks alternating between convolutional and pooling, the number of feature maps are increased, while the spatial resolution is reduced compared to the corresponding previous block. The additional layers of CNNs are the following. Considering a neuron as a fundamental unit of a neural network processing, we describe one of its basic elements, an activation function. Hyken defines the activation function as a restriction of the output amplitude of a neuron, having an output interval generally of a unit interval from 0 to 1 or from -1 to 1. The sigmoid function is the most common activation function. However, the recommendation for modern neural networks is a rectified linear unit, ReLU, because being a nearly linear function, they preserve many of the properties that make linear models generalize well. The minimization of the loss function is the quantification of the concept of learning. Using the loss function as a parameter to the optimization process, several algorithms can be applied to diminish this loss. Gradient descent and its variations are the favorite methods for this task. And finally, the theory of regularization helps to reduce overfitting. L2 regularization, or wave decay, adds an extra parameter to a cost function. The effect of regularization is to make the network prefer to learn small waves, all other things being equal. Going a little bit into the related works, the first paper to use CNNs trained by backpropagation were proposed by Ian LeCun in the 90s, and it was a breakthrough in the field with the presentation of LeNet 1. In 1998, LeCun published a paper reviewing various methods applied to handwritten character recognition and compared them, showing that CNNs outperform all other techniques. It also proposes an evolution to the original LeNet 1 to LeNet 5 model. In 2012, Krzyzewski revived the interest in CNNs by showing substantially higher image classification accuracy on the ImageNet challenge, almost half the error rate for object recognition at the time. Likewise, the increasing hardware processing capability and the popularization of graphical processing units, GPUs, were an additional asset to the works. Starting to increase the architecture's depth, this work of VGG explores the addition of convolutional layers with small convolutional filters. Of all the investigated networks, two had the top results, VGG 16 and VGG 19. With 27 layers, Inception is a network with a great number of parameters that try to work around the overfitting issue. Besides the traditional convolutional and pooling layers, there is the addition of an Inception module, a module that analyzes the correlation statistics of the last layer and clusters them into groups of units with high correlation, forming the units of the next layer and connecting them to the units in the previous layer. With more layers than the previous, ResNet showed up as a residual learning framework that improved the training of deeper networks. With the network depth increasing, accuracy gets saturated and then degrades rapidly. This degradation is not caused by overfitting, and adding more layers to a deep model leads to higher training error. To address this issue, they explicitly let stacked layers fit a residual mapping. In 2014, Karpathy extended the image recognition good results to video classification, developing a network structure with two different inputs to the classical CNN. Noticing that the standard video classification approaches consisted in involving three main stages: visual feature extraction, feature combination, and then classification, and that CNNs were achieving state-of-the-art results on image recognition, segmentation, detection, and retrieval. A new technique that included local motion information in the video as connectivity to a CNN architecture was suggested. And as stated by Ross Gershik, features matter. Bringing the multi-stream concept from video classification to image classification, we can input almost any extra information in the other streams, such as a segmented version of the first input or a crop of a region of interest. In Karpathy's two-stream architecture, MCNN, they used AlexNet as a base. From this AlexNet, three different architectures were proposed: late fusion, early fusion, and slow fusion. The late fusion architecture places two or more single-stream networks with shared parameters and then merges the two streams in the first fully connected layer. Therefore, the first fully connected layer can compute global features by comparing the outputs of both towers. Although it looks similar, the early fusion model combines information across an entire time window immediately on the pixel level by modifying the filters on the first convolutional layer in the first shown model. This connectivity allows the network to precisely detect local motion, direction, and speed. The slow fusion model is a balanced mix between the two multi-stream approaches that slowly fuses information throughout the network, such that the higher layers get access to progressively more global information in both dimensions. Simonian proposed a two-stream architecture for the purpose of receiving the spatial and temporal components of a video. Each stream is composed of a deep CNN. All hidden wave layers use the ReLU activation function, and the fully convolutional layer is combined by using the previously cited late fusion. In this work, two fusion methods are considered: averaging and training a multi-class linear SVM. The initial step of this dissertation, was an exploratory methodology. As a primary reference source, we use books, conferences, and journal articles. As secondary, survey articles and participation in conferences in the area of AI and computer vision were used. This phase was fundamental to understand what difficulties and benefits the area is going through. After the bibliographical survey, it was possible to verify that the scope of CNNs has been gaining more and more space among the scientists, and that special attention to MCNNs has been given since it was an approach that could handle more features at once. Besides being exploratory, the proposed methodology is also sequential. The following steps were taken. An extensive bibliographic review of CNNs and MCNNs was performed to discover the main gaps in the literature and define the line of work to be filled by this dissertation. And in addition to the previous steps, the implementation of the networks above for different applications such as image and document classification was made. This step was also fundamental to understand how the main frameworks and APIs work. Moreover, the first contributions were produced. While we constantly note that the gain in accuracy, sometimes this gain was not that significant or required a computational power that was too high for us to be able to start the experiment with multiple inputs. Thus, one way to continue applying this technique was to investigate fusion points that would increase accuracy with less training time and would not increase the network parameters to make it impossible to run tests. After all, the definition of the problem took shape, and we could identify a central gap in the literature where to fuse MCNN models. Also, we had the restriction of not having infinite computational power to run experiments. Considering the restrictions and that the ReLU activation on convolutions is widespread and its implementation is very simple, a fusion strategy for any model containing ReLU's activation was proposed, developed, and tested. Traditional datasets were used to validate the novel method. Further, we also analyzed our proposition with a complex image classification dataset called NORB and expanded the implementation to object detection using the BDD 100K dataset. While designing the new module, we observed that our strategy was able to boost results from outdated architectures, making them competitive again. As a consequence of this behavior, we were able to compare the implementation of our technique both in more traditional, no longer used models and in more recent models. The importance and great impacts that multistring CNNs were previously exposed, and knowing the improvements that all papers seem to share, such as performance boosts when compared to single-string models, faster runtime and convergence, some application studies were made, and they are our initial contributions. Autonomous driving and navigation technology in autonomous vehicles is an artificial intelligence application that has drawn great attention with the popularity of intelligent cars. We propose here a MCNN capable of estimating the steering angle of an autonomous vehicle, having as only input images captured by a camera attached to the vehicle's frontal area. Following a single-stream CNN architecture, we propose a multi-channel model that processes the inputs in different channels or streams until the last exponential linear unit layer. In other words, the outputs of the last ELU layers from each channel are concatenated and passed as input to the first fully connected layer. 5 model combinations were designed. Model 1 was the original single-channel CNN. Model 2 used the two-channel CNN architecture, receiving the original image and its frame subsampled in 50%. Model 3 also used the two-channel CNN, but it received the original image and its central region. Model 4 uses the three-channel architecture, aiming to observe whether the neural network can produce better results if the additional information is combined with the original frame. Another model, Model 5, containing only the generated versions of the dataset, was also evaluated. It's possible to observe here that Model 3 trained with 350 epochs and obtained a lower NRMCA when compared to the others, including the single channel as a reference model. It could also be seen that MCNNs provided significant improvements in their use in autonomous vehicles application, with an approximate improvement of 7% than to the reference model. Furthermore, Model 5 presented similar results to the others, showing that it was capable of maintaining robustness even when receiving an input with reduced dimensionality. Plant diseases are considered one of the main factors influencing food production, and to minimize losses in production, it's essential that crop diseases have fast detection and recognition. Here, we propose the use of MCNNs based on two distinct single architectures, AlexNet and GoogleNet, or Inception v1, to train and evaluate the plant village dataset. Different versions of the original dataset were generated in an attempt to prove the contribution of these additional streams to the network performance. The extra streams consisted of a grayscaled and segmented version of the color data and were combined as version 1 color plus grayscale, version 2 color plus segmented, and version 3 grayscale plus segmented. It should be noted that knowing the gains of transfer learning techniques, we choose to train from scratch in order to demonstrate the possibility of customization and gains in the learning process compared to a sample considered small for a dataset. Also, the additional inputs of the network provided better accuracy than the single stream network, showing that MCNNs were able to enhance the general system, generating the best overall result in this work and keeping the mean F1 scores regular and robust, independently of the chosen model. Um, Nowadays, the Brazilian court system is currently the most clogged up judiciary system in the world. We have like thousands of lawsuit cases reaching the Supreme Court every day. These cases need to be associated with relevant tags and allocated to the right team. The extracted text from the lawsuit's PDF files is the input of a by LSTM model. In order to combine two domains, ResNet was fused to the original by LSTM using the PDF image files as input. Here we have the classification report using only text as input, disconsidering totally the image feature. And although the results with only text were already excellent, we can see that the inclusion of image features, which alone did not work, were essential for a significant gain in accuracy. Thus, we expand this concept and present it next. Still dealing with the problem of the overflow of cases in the Brazilian judicial system, we explored multimodal classification of documents from Brazil Supreme Court. In here, we used a subset of Victor dataset named Small Victor. By combining these two different sources of information previously extracted from individual classifiers, ResNet 50 for image classification, and a stack of convolutional neural networks for text classification, we create a fusion module that is capable of handling absent textual or visual inputs by using learned embeddings for missing data. The table presents results for text only, image only, the fusion module with sequence classification, and the reference layout LMV2 model. Several other approaches were implemented before reaching the final fusion model that concatenates each modality embedding followed by fully connected layers. Primarily, the combination of raw images with raw text that Was the same strategy used in the aforementioned paper was tests. However, since we had a distinct subset with more refined data, the results were not as good as the previous one and could not solve the same issue. Continuing the process of classification improvement using the Fusion module, the order of the pages was also part of the solution. Sequence classification techniques as a conditional random field (CRF) were used to output a sequence of class predictions. And now we arrive at our proposed topology. We saw that the fusion stage can be performed at a convolutional layer without loss of performance. Based on this, we propose a novel model based on a new cross-fusion method applied for all available models of MCNNs. This new proposed cross-fusion method is focused on observed features, specifically in the ReLU stage, used by many of traditional MCNNs, developed in all known approaches. Our novel proposed model is based on a crossing signal inference among each data streaming, or channel, output from the convolution stage and processed by the ReLU stage, connecting each of these outputs with other outputs coming from all other data streamings, using a new fusion function approach. In system analysis, there is a field that studies the enhancement or restoration of degraded signals, inspired by the fact that there is no signal processing without degradation and that a CNN signal suffers loss along its course. We decided to apply basic signal operations between activation layers, especially the ones that use ReLU, used by many classical MCNN models developed in several popular approaches. ReLU outputs 0 across half its domain, making the derivatives through it remain significant whenever the unit is active. Nonetheless, they cannot learn with gradients near 0. To boost up near zero gradients and get a hold of important features that may be left out, we combine two different signal streams and a crossing signal inference of the operation result to the input of the subsequent layer. The equation presents a fusion of two signals with a previously chosen mathematical operation. The fusion modules defined by the equation and this illustration are repeated along with all CNN's convolution ReLU layer sets, finishing with a late fusion process right before the fully connected step. This figure presents a visual definition of this proposed cross-fusion strategy. The chosen testbed dataset to evaluate our model was the CFAR10, a popular image classification benchmark dataset. For a multi-streaming scenario, the selected inputs were purposely worsened to evaluate the robustness increased by the proposed LCNN model. The main goal here is not to achieve or improve state-of-the-art results. In the first string, a grayscaled version of CFAR10 is used, and in the second string, an edge extraction created with a canny edge detector. To evaluate our approach, our cross-fusion function is set to an average operation, and the use baseline single and dual string architecture is AlexNet. To compare performances, we also implemented a late fusion multi-stream AlexNet called AlexNet MCNN, consisting of two independent streams that merge right before the first fully connected layer. Additionally, for comparison purposes, we also evaluated a cross-model CNN called AlexNet XCNN, which is a typically image-based approach that each of the input image receives its own CNN superlayer, with cross connections inserted after the pooling operation and full wave sharing in the fully connected layers. This model was developed to explore the crossing signal inference, and its accuracy performance will be used to compare with our novel proposed LCNN model. Results here also consider the traditional single-string AlexNet architecture for both of our inputs. In the first string, a grayscaled version of CIFAR10 is used, and in the second string, an edge extraction with Canny detector of the first string. The plot here confirms that our edge detection signal does not add consistent information to the network, as expected. Further, the grayscale string does not have a good performance by itself. Using this information, we can also point out a stability from the AlexNet LCNN, achieving its peak about 50 epochs and maintaining accuracy and loss during all the training process, unlike AlexNet XCNN and even AlexNet single string for grayscale. Moreover, our fusion model was able to increase the network robustness results by using poor signals as inputs. In our test expansion of the previous technique, two additional mathematical operations to the average were implemented in our fusion model: addition and subtraction. Further, we adapted 9 different architectures backbones to demonstrate that the lattice strategy has significant improvements with varying kinds of structures, varying in depth, in number of convolutional layers, and parameters in general. Initially, 3 sets of data were used to evaluate our fusion strategy: the previously used CIFAR10, CIFAR50, and CIFAR100. Different sizes of datasets were chosen to analyze our strategy performance with a distinct amount of data samples. To create images for the second stream input, we generated a mirrored input using an edge extraction created with a Canny edge detector. With the need to expand the test, however, it became necessary for us to include other data sources with different purposes. The main goal of the NORP dataset is to recognize 3D objects from shapes, while PDD-100K is the largest open driving video dataset containing bounding boxes annotations and an object detection challenge. The CIFAR datasets had their training set subsampled in a cross-validation procedure with 5 folds. The following accuracy results are presented by fold. No data augmentation or transfer learning was used in the whole process. Due to many experiments, we chose to gather all accuracies in one figure. And in all plots, the color blue will represent a late fusion version of the network, and colors orange, green, and red are the L fusion architectures, with average sum and subtraction operations. Focusing here on one backbone, we reaffirm that the goal of this work is not to beat any kind of state-of-the-art models. Thus, it is remarkable to achieve strong accuracies with very degraded inputs. A late fusion AlexNet went from 42.69% to 58.66% using the CIFAR-10 dataset. AlexNet has a very straightforward backbone. It's easy to implement and can run smoothly on plain hardware. And after the experiments with variant and degraded CIFAR datasets, we decided to understand our proposal better by applying our method in a real and not overused dataset. This table presents a comparison between three different size architectures in three forms: single string, multi-string with late fusion, and multi-string with our lattice cross connection for the NORB dataset. Results show that at least one lattice operation could outperform all other results, demonstrating the flexibility of the technique when we come across not so good results. The BDD 100K and the LFR-CNN brings complexity and a challenge to our strategy. On the network aspect, we are dealing with two different outputs with distinct goals and implementations. On the data side, we have a very difficult in the wild dataset that is completely outside the scope of what we were evaluating in the models. Here we have actual driving scenes. Using the work of Bhargava as the baseline reference, since it uses the same model and backbone as ours, we report a mean average precision at 75% improvement of 50.16%. This improvement was obtained after training per 50 epochs without loading pre-trained waves or parameter optimization. A closer look at this plot shows that the loss drop tends to diminish if trained for a longer period. However, since we had computational limitations, 50 epochs were our maximum effort here. The first applications presented here showed a more straightforward way of constructing MCNN, simple network constructions for complex applications. The results all seem to improve a single approach, leading to the hypothesis that networks with multiple entries were naturally good candidates for solving different problems. With the proposition of the L strategy, we start to raise the level of our efforts. The lattice fusion comes directly with a new modeling structure as we begin to customize more previously consolidated networks. Primarily, we use an AlexNet architecture as a baseline and CIFAR-10 dataset and implemented three different model versions: a multi-string CNN with late fusion, a cross CNN, and our lattice CNN, alongside two single strings of traditional AlexNet. Experimental results show that the proposed L lattice module outperformed all the models above at least 28% compared to all tested models. Also, the proposed fusion demonstrated robustness and stability, even when distractors were used as inputs. With the expansion of the test, we use other different backbones and 4 datasets, including the CIFAR-10 mentioned above, to demonstrate the robustness of the proposed technique. Our experimental results show that the proposed strategy has faster convergence and flexibility of operational switches. The previously noted stability was maintained. Considering Considering that we stayed in a safe field during all the anterior applications, we managed to elevate our strategy to a new complexity, object detection. Here we have to not only classify, but we also have to locate an object during a video. That is a task that requires two output, and it is indeed another layer of difficulty. Nevertheless, the L strategy still performed well with the restricted training conditions and our initial assumptions of not using pre-trained waves, not recalibrating the hyperparameters, and not doing fine-tuning were preserved. With a gain of approximately 50%, we are positive that the suggested implementation can go even further. There is a possibility that the described module and its default operators will over-amplify signals in a way that the model will simply not learn. Using signal processing knowledge, we know that when this kind of peak occurs, we can perform a compression to approximate low and high signals. Therefore, we propose using a logarithm-based compression function that will balance the broad range, reducing the difference between large and small values when my L strategy does not improve the results. An example here is our LVGG16 implementation. Our first run using average function went well, but not well enough to beat the MVGG16 architecture. Further runs with other defined operators were boosting both tensor streams, and our model found its local minimum very fast without room for optimizations. The technique mentioned above was meant to be used with all the full hyperparameters. Still, it does not work well for all situations. A VGG19 with standard initialization will continue to have its signal over-amplified, converging too quickly. Nonetheless, basic optimization approaches are sufficient to train the network smoothly, gather all accuracy. The learning rate, for example, controls the adaptability of the dataset to the network and affects directly in waves update. This work explores how multi-string deep neural networks are a game changer in the deep learning field. However, they have not been extensively researched yet. We came across many gaps in this kind of building during our study sessions. Where is the best point of fusion of several equal or different backbones? What techniques can we use to get the best results from this inclusion of features? Do all backbones work the same when it comes to fusing them? With the LCNN model, we could at least clarify some of these questions. Using signal processing fundamentals, we developed a general module to get the best that multiple signals could offer us by over-amplifying our inputs and crossing them to serve as the new input to the sequential convolutional layer. Nonetheless, we also observed that when the strategy fit well the backbone, the results were likely to be more expressive than the single versions or the late fused backbones, regardless of the final application. This observation included elementary structures such as AlexNet or previously considered state-of-the-art networks. The expressiveness led to an exciting conclusion. Our L strategy can give extra life to obsolete models, offering an uncomplicated module design to basic structure, allowing them to become competitive again. This model recycling is especially interesting when the available hardware capacity is not enough to train the super complex models that come out almost daily. Our goal to reuse previous state-of-the-art architectures with few modifications to keep them in the game was successfully achieved. In other words, the L strategy module can make older models usable for brand new challenges. Still, there is no definitive technique. The general model the general model turned out not to be suitable for certain types of architectures. The L strategy with very large kernel sizes tends to overamplify so much the signal that the default hyperparameters are not enough to train a good model, causing the process to get stuck right on the beginning of the training cycle. We showed that we could obtain an increase of accuracy up to 63.21% in image classification tasks using an easy implemented network and a boost of 50.16% on the mean average precision baseline of an object detection challenge with a classical model structure. Besides dealing with the overamplification issues, future work will also include new steps exploring improvement categories. The next move is to enhance a range of other models. Additionally, we intend to explore not only CNNs but also every kind of structure that includes a ReLU activation, such as long short-term memory (LSTM) and generative adversarial networks (GANs). And different application tasks are also considered when we explore distinct types of architectures. Since this module presents implementation flexibility, we plan to test the number of fusion modules needed to improve the final network representation, considering that not all ReLU activations need to be crossed. Finally, among the improvement and development activities, the need to create an automated strategy for the LCNN conversion of existing models, including those in disuse, is worth mentioning. Here are some already published papers reinforcing the importance of our work. We are producing since 2018 and we have a good reception of these works until now. So here is the bibliography that we use to create this presentation. And I really would like to thank you all for accepting the invitation and to believe in my work. So thank you very much.